My topic is finite element modeling coordinates and shape functions. Introduction of finite element modeling coordinates and shape functions. Finite element modeling is a numerical technique used to analyze complex structures by dividing them into smaller, simpler elements. Finite element modeling is a numerical technique used to analyze complex structures by dividing them into smaller, simpler elements. The coordinates of these elements play a crucial role in defining the geometry and connectivity with the modeling. The coordinates of these elements play a crucial role in defining the geometry and connectivity within the model. Shape functions are mathematical functions used to interpolate the values of a field variable within an element. Cartesian coordinate system. In Cartesian coordinates, each point in space is defined by three orthogonal axes x, y, and z. Cartesian coordinates are commonly used in finite element modeling due to their simplicity and ease of implementation. The shape functions in a Cartesian coordinate system are typically simpler compared to other coordinate systems. Natural coordinate system. Natural coordinates are local coordinates defined within each element, making them independent of the global coordinate system. Natural coordinates are particularly useful in finite element modeling as they simplify the calculation of shape functions. Natural coordinates are particularly useful in finite element modeling as they simplify the calculation of shape functions. Shape functions expressed in natural coordinates allow of easy interpolation of field variables within an element. There are three types of orthogonal coordinate systems. Cartesian coordinates or rectangular coordinates. Second one, cylindrical coordinates. Third one, spherical coordinates. Isoparametric mapping. Isoparametric mapping is a technique used to relate the natural coordinates of an element to its physical coordinates. Isoparametric mapping is a technique used to relate the natural coordinates of an element to its physical coordinates. Isoparametric mapping ensures that the shape functions accurately capture the geometry and behavior of the element. By using isoparametric element, one can achieve higher accuracy in finite element analysis. Isoparametric quadrilateral elements. The answer to this problem is isoparametric degrees of freedom. Degrees of freedom are the independent parameters that define the state of a system at a particular point in space. In infinite element modeling, each node in the mesh has a certain number of degrees of freedom associated with it. Infinite element modeling, each node in the mesh has a certain number of degrees of freedom associated with it. The choice of degrees of freedom can significantly impact the accuracy and efficiency of the analysis. Shape functions in 1D elements. In one-dimensional finite elements, shape functions are typically defined as polynomials of the natural coordinate. In one-dimensional finite elements, shape functions are typically defined as polynomials of the natural coordinate. These shape functions ensure that the field variable can be interpolated accurately within the element. The shape functions ensure that the field variable can be interpolated accurately within the element. The choice of shape functions affects the accuracy and convergence of the finite element solution. The choice of shape functions affects the accuracy and convergence of the finite element solution. Shape functions in 2D elements. In two-dimensional finite elements, shape functions are often defined as products of one-dimensional shape functions. Shape functions in 2D elements allow for the interpolation of field variables over the entire element domain. Shape functions in 2D elements allow for the interpolation of field variables over the entire element domain. Higher order shape functions can capture more complex variations in the field variables. Shape functions in 3D elements. In three-dimensional finite elements, shape functions are typically defined as products of 1D or 2D shape functions. 3D shape functions enable the interpolation of field variables in all three partial directions. The complexity of 3D shape functions increases within the order of the element. Lagrange's versus serendipity shape functions. Lagrange's shape functions are defined at the nodes of the element and ensure interpolation accuracy but may lead to numerical difficulties. Serendipity shape functions are defined at the element edges or faces and offer improved numerical stability but may sacrifice interpolation accuracy, element distortion, and shape function quality. Implementation challenges and best practices. Implementing accurate and efficient shape functions in finite element modeling requires a careful consideration of various factors. Conclusion. Finite element modeling coordinates and shape functions are fundamental as numerical analysis in engineering and science. By understanding the principles behind coordinates and shape functions, engineers and researchers can effectively utilize finite element modeling for a wide range of applications. Thank you.